Hi. Welcome to buffers. Okay. What is a buffer? Do you have any idea what a buffer is? No.
It's acid or concrete.
Well, oh, that's very nice. See, we're doing acid-base equilibrium. And a buffer is something you can add to an acid or a base such that that acid or base will resist change. Now, one important use for buffers would be like our bloodstream. Our bloodstream is highly buffered. The reason why is if we have a little bit of like vinegar or lemon juice, you probably don't want to die. And of course, if you didn't have buffers in your bloodstream, you would eat a lemon, your pH would drop to like 4, and peace out. That's not a good thing. Okay, so buffers basically just resist change, right? They resist change in pH. So a buffer, we probably learned about weak acids. And if you have a weak acid, you can pull the two ions apart, the H plus and like let's say the C2OH2 minus or whatever that is, the anion, and add that to a salt like Na, right? And then we learned that if we have a salt, we can determine whether it's an acid or a base. Now in this case, we learned that a weak acid has this second part, this conjugate base to it, and that conjugate base can come hitched along in a salt, and you can add that salt to the acidic or basic solution, and that's basically how you make a buffer. Okay. So if you imagine this weak acid, what would be an example of a salt for HF? The salt would be, well, what's the anion? Do you know the word anion? The negative part. Which is the negative part? So F, okay. And can you imagine this F hanging out with some other like cation? Well, F is a minus, so Na. That's your salt, okay? If NaF is the salt, we say that F is the common ion. So that's just a word that I want you to learn, common ion. Okay. So how does this all work? Now imagine if you had 1 molar HF, okay, and so 1.0 molar HF is weak. So are we going to just assume that it dissociates completely and use molarity of HF to find the molarity of H or F? Or do we do our special little friend? Which is, yeah, so ice has not gone away, not yet at least, and that's what we're going to need, okay? However, keep in mind that let's say we have 1 molar. What's going to happen there? Well, yeah, we're going to have 1 molar of Na plus. Oops. And 1 molar of F minus. That one does dissociate completely. So if you imagine for a second, the only way that this is going to change our ice table at this point, any guesses? The only way this is going to change our ice at this point is is via the I, right? I is going to be affected because we no longer have, well, okay, we can do this, right? 1 molar, and that would be our HF. And then usually, what would I put here for my H plus? 0. Is that still going to be true? Yes. And then we have our F minus, and normally my F minus will also be 0. In this case, is that true? So Jocelyn said yes. Now we start with 1 molar. So that's really all there is to this situation. And, you know, we can do the rest. You know, you've got 1.0 and then 0, but here you're going to have, of course, 1.0 molar. So that situation is going to be there. So it changes the end a little bit. Of course, if you ice as usual, you get pH is 3.14. So what's going to happen if we add a bunch of, let's say we keep adding a bunch of H plus? What's going to happen conceptually if I start adding H plus to this particular situation where we have a bunch of F minus? Is the H plus going to increase the pH, or should I say make it more acidic, which would be a lower number? But would addition of H plus change my pH, or would something else happen? So adding H plus would cause, you would expect the pH to change, yes? Okay. Anything else that is possible? Didn't we call this a weak acid? And as such, we have, remember again, up here, we have all this excess what'd you say? Fluorine, good. You got excess fluorine. You have extra fluorine. Why do we have extra fluorine? Because we added the salt that was sodium fluoride. And what does the fluorine do in a weak acid? Okay, well, it's going to react. Okay, is this getting crazy for you? Okay, they're going to combine. It's a weak acid. H and F love each other. I miss you, fluorine. I miss you, hydrogen. And they're going to get together because they're a weak acid. I can tell on your tests that you understand that in some sense. You understand the weak acids mean that H's and whatever their conjugate bases are will stay together forever. They have a strong bond, which is weird. I said way earlier in my previous video, when I call something weak, I'm actually calling it strong. Get used to that. And I think you are used to that from what I can see. Okay. So if you have extra F in there and you put H in there, they're like, I miss you. I miss you. And is the pH going to change if H and F are combined together?
No.
Not really. So what we say is that this whole situation here is going to cause a resistance in change. You understand? So adding the F resists the change associated with adding H pluses. Now conversely, what if I add a bunch of OHs? Well, but we're a buffer, right? So you can probably guess that the answer is that I'm not going to change the pH, because that's the whole purpose of my buffer. So thinking about that when we do buffers, thinking about the whole purpose of a buffer is to resist change. How are we going to resist change when adding a bunch of OH minuses? Okay, so thank you, Kyle and Kate. Yes, if water will form, it will. Okay, so I'm adding OH minus, and you know, pretty much as usual, the addition of OH will consume more H's as always, and that's just something that always happens when I add a base to the situation. Water, if water can form, it will. And if you start adding a bunch of OH minuses, you're going to start eating a bunch of H pluses. And that's the only time when F is going to be like, where are you going, H plus? And be like, I found somebody new. Right? And H plus is like, bye, Felicia. And they're like, why? Who's better than me? Well, water. You know, water's the winner. Yes? Comprender? Okay. So real quick, I'm going to introduce you to the Henderson-Hasselbalch. It's kind of like tenuous as to how this equation is going to be used on the AP exam. They're like, you don't need it, but then they may be like, well, what does this equation mean? So then, you know, we'll find out later if we really, really, really need it. But it's also kind of useful. If you actually know, and when I say when you know the acid conjugate base pair ratio is known, why do we know how much conjugate base we're starting with? Well, in this case, since it's a buffer, we know how much conjugate base we're starting with because of, so we know the conjugate base, right, because of this whole situation here. We know how much conjugate base we have because we added it in the first place. And so that being said, for this particular type of problem, we can use something called the Henderson-Hasselbalch equation because we know how much of conjugate base we have. And here it goes. So, blam, this equation. And this one you can, you know, do in a calculator all at once, right? If you know, so what the heck is this? Well, that's easy, right? You just take your Ka and you take the negative log. And then this, I put base and acid here because I'm essentially telling you that if you know the concentration of base and acid, because it's a buffer, you just plug them in, hit that log, and add it to the negative log of Ka. Okay, so it's kind of a shortcut, and you'll see when we can use it. And then conversely, of course, we can say POH equals PKB plus log of conjugate acid over base. Okay, so I have doubts as to whether I kind of wrote this right, but the idea is the same, right? You have the base on the bottom. You're not going to see these very often, but you'll have the base on the bottom, which that looks like a pretty legitimate generic base. Criticize me later if you want. And then the conjugate acid of the base, which that should be the conjugate acid of the base. Kill me later. Okay. So those are the two versions. Obviously, we'll definitely maybe see this one. Probably definitely not. Maybe see this one. All right. So if we're going to do a problem for buffers, we got to roll out this whole, like, roadmap situation. Yay! So a buffer problem is going to change the situation a little bit. Okay, we used to just get the givens and then go ahead and just find the pH. Well, in this particular problem, we're going to find the pH for the buffer first. Then we're going to add a bunch of chaos, right? Adding H's or OH minuses. And then we're going to use stoichiometry to find a new I and then do it again. Because we basically want to see if adding our H's or OH minuses changes my buffer a little tiny bit, or, of course, you must understand that buffers eventually give up. And so if we add too much acid and base, you can't go drinking a bunch of hydrochloric acid and expect to live, right? At some point, the buffer gives up, and you die. Okay, so that's kind of like a roadmap, and let's do an example problem here. So there's my problem. I've got my NaOH being added to my weak acid, trying to disrupt equilibrium, and we've got my acid of the conjugate base, or yeah, of the weak acid, resisting that change because we've got a bunch of conjugate base in the salt there. So we're going to try to add chaos, but we're going to try and stop it. Okay, so the first thing we always do when we're doing a problem like this is we list all of the things that are in there. Okay, so this is, now remember earlier I had said use stoichiometry right here. Okay, so we're going to have the stoic step is what I'll call it. Okay, so when I say stoic step, you say yay. I say stoic step, you say yay, stoic step. Okay. So, stoic step.
Yay.
Thank you. All right, so that'll be back. Okay. Now, step one, you want to find out by listing ions. You want to find out what's going to happen, right? So this is kind of like an exercise in looking at the big picture. What are we going to have in my beaker once we add stuff in my beaker? So we know we have these two ions because salt dissociates, right? You with me on that one? Salt dissociates. So we know that these things will, supposed to be a comma. And somebody said water earlier, but water's not really going to affect the situation at all. And then H plus. Okay. Is H plus going to be a dominant player in this game right now? Why? Where's all the H plus at? Where the H plus at? Where the H plus at? Where the H plus at? Okay. The H plus is not there because we're dealing with a weak acid. When we have a weak acid, the H pluses are busy with their friend, the conjugate base. So we don't say H plus is going to be a dominant player in this game at this point because he's got a friend. So what other molecule would we see in large amounts in this beaker? Huh? Not there yet, but what else? That guy. Because that's what's in there, right? So we've got that's important, that's important, that's important, and we have one more being added in huge amounts here. That is the one that is causing all the friction, all the problems. Yeah, so you can say, you got to say OH minus though. If you say NaOH, again, the NaOH dissolves, it dissociates. So we just have Na plus, just like we have here, and then OH minus. So that's what we have in our beaker. So if you remember, as Katie says, so you're supposed to say, like, okay, what will happen? Step 2 is, what happens? So here's our equation. Number 2, Caitlin says, I'm sure you've heard this before. If water will form, then it will form. And that's exactly what you have here in number 2. You've got my weak acid, which normally will just hang out and be by itself, all happy and stuff. OH comes in, and somebody asked the question, what's the deal with that? And OH minus, like, steals the H's, right? It knocks them out and takes it, okay? Because H2O, as we learned before, has a very low K. It's the weakest acid you could possibly think of. And so that's going to happen first. And by listing the ions here and looking at the equation here, we can do something for an ice table. But this initial stoic step, yay! Forgot Kyle. So this initial stoic step has something called ICF. Okay, so there's there's an ICF table, and you'll see why we have this whole thing here. Remember, the whole point of this step is to keep track of what is going to get consumed. So the obvious answer would be yes, something's going to be consumed. The harder answer would be what is going to be consumed.
And you can see the OH is consumed.
So after all the civil unrest happens because of the OH minuses that come in, you got your OH minuses, okay, they come in and they're going to be used completely, reacting with C2H3O2 and taking all of the H's from H3O2, okay, and going to completion. After all these are gone, then you're going to end up with 0.49 moles, no more OH minus, and of course we made 0.51 moles of conjugate base. All right. Now, unfortunately, Sarah, this is the best time to go back to molarity, right?
Oh my god.
Yeah. So now that we have to go back to molarity, how do we do that? Divided by the liters, and after we mixed everything together, how many liters did we have? We're still at 1 liter, right? Aren't we?
1.01.
Probably just a liter. Which is good because, you know, now the answer is just 0.49 molarity. So, we had 10 milliliters added to the 1 liter. 10 milliliters is 0.01, and that would make 1.01 liters. But we're not in 3 sig figs, we're in 2 sig figs, so feel free to ignore that. All right. How do you know? And so now we move on to the I step, because now we have a bunch of molarities, yes? So now we can think, well, what happened to all the OH minus? It was used, okay? Now the OH minus is gone, you understand? It's gone, disappeared, all used. So we write a last equation, which we know of as being this, or we could know. My writing's going to be less precise, I think, with this other stylus. Just write bigger, I guess. Okay. So now we have that equation. Hopefully you understand where that came from. The OH minus is gone. Now the OH minus is gone, the weak acid is going to do what it always does, and we just do our simple ice table. And there it is, remembering, of course, that this 0.51 molar came from up here, whereby we made some more conjugate base, right? We made some more conjugate base. Well, we started with 0.5 molar. Now we have slightly more 0.5 molar. And what's next? Yeah, again, we're going to assume x is so small we can ignore it. And that totally simplifies my expression. pH is going to be equal to 4.76 if we work this out. And if we were to do the percent dissociation trick, okay, we would get, it would work.